All right, welcome to EngFiz2P04's practice problem video for general elasticity, the final topic in EngFiz2P04. We're going to be doing the problem that was test number 11 in 2019, and the problem goes as follows. You have a 10 centimeter cube that's made of a material with this stiffness matrix. So this is the stiffness matrix, which is the one with the C components, the one that directly needs to be put into FlexPDE. And it asks us first, what do the -8 gigapascal components do? Then if it's constrained to have no displacement in the y direction anywhere, but free to move in the x and z directions, and its two x surfaces are each given this stress, find all the resulting axial and shear strains and the y stress that arises in the center of the material using Maple, and then in FlexPDE, and then it asks a conceptual question: should the stress and strain be uniform? Why or why not? This is one of the things that we could be solving with this. In general, the concept questions that you can do with this topic are listed at the start of this problem set, which are be able to determine stiffness or compliance Voigt matrices given either the other matrix or the E and nu components and told that it's isotropic, or information to determine that it's isotropic, like maybe it has no crystal structure, or it's like a glass or something, that's going to be isotropic. Or given appropriate parameters for orthotropic materials, so you're told it's orthotropic and given the right parameters, figure out the stiffness and compliance matrices, or given the rank 4 tensor component, so not even in the Voigt notation, but convert it to Voigt notation. Or perhaps determine any of these above things given one of the matrices in Voigt notation. Or you could be asked to determine what symmetry a material has given one of its matrices. So by looking at the matrix, can you tell what kind of symmetry it has? What about the stress and strain components? Can you figure out those things, the components of stress or strain, given sufficient boundary conditions and stiffness or compliance Voigt matrix information? This is what the practice problem that we're tackling today does, is it asks us, given this matrix, what are the components of the stiffness of the stress or strain, right? So given the matrix, what are the stress and strain components by hand and with FlexPDE? That's what we're doing principally in the first part of this problem. Determine beam deformation subject to various boundary conditions using FlexPDE given stiffness or compliance matrix information. This is kind of like perhaps repeating the stuff from combination elasticity at the end of the torsion section, but for anisotropic materials, or even repeating the bending section, or the shear section, or the axial stress section stuff, any of those things that went into combinational elasticity, or even beam resonance stuff with effective stiffness that you can determine for an anisotropic material from the stuff from this week. And then finally, be able to explain anisotropy resulting from different components. What is it that the 2,5 component does in this problem as asked in part A? To understand what these off-axis components do, it's helpful to go back to where we introduced Voigt notation and take a look at where the stiffness matrix transforms strains to stress. So in this particular situation, when we have -8 there, this is the 2,5 component. So this in general is going to be mapping what? It's going to tell you the y-axial stress from the xz shear strain. So the 2,5 component of the stiffness matrix tells you that xz shear strain is going to require axial stress in y, other things equal, for it to be maintained. So if you just you do whatever you need to do to the material to put it into xz shear strain, and that's going to be linking to compressive stress in the y direction if you have a positive xz shear strain. Conversely, this part, the 5,2 component, tells you that if you have, taking this vector and dotting it with this one, a y-axial strain, a normal strain in the y direction, that's going to be leading you to xz shear stress, other things equal. So xz shear stress is going to be decreased, developing a negative xz shear stress. Not sure if we want to call that compressive or tensile for shear, probably not quite clear to do that, but a negative XZ shear stress if you have a positive strain in the Y direction axial. So that's what the 5, 2, and 2, 5 components do in this matrix. They couple the axial Y and shear XZ strains and stresses together. So next up, if the material is constrained to have no displacement in the Y direction anywhere, which means no V component, V is equal to 0 in any one of the terms that are making up the derivatives that go into strains, but is free to move in the X and Z directions, and its two X surfaces are each given a compressive stress. So if it's free to move in X and Z, that means we are going to be allowing whatever displacements need to happen in X and Z. So the strain here is unknown, the strain here is fixed to 0, strain here is unknown, and the other strains, let's see, YZ is still unknown because even though there's no V, there could be W. So we could have W displacement per step in Y. And you could have here for XZ, even though V is unknown, you don't have any V, so there's no slope of V per step in X. You could have slope of U per step in Y. So this one and this one are not necessarily 0 just because you have no displacement in the Y direction. That does fix this to be 0, but it doesn't by itself fix any of the shear strains to be 0. If it's free to move in X and Z, and we're not going to be resisting that, that says that the X stress is equal to 0, the Z stress is equal to 0. What else? Does that tell us anything about the shear stresses? We're not resisting it moving in X and Z, so that says that the shear stresses are 0, except for the one that we're actually applying. So actually X stress, saying it's free to move in those dimensions doesn't necessarily mean the stresses are fixed. It does mean that these stresses, sorry, I said that backwards. I jumped ahead a bit there. It doesn't mean that the stresses are 0. It does mean that the stresses are fixed. If you're applying a fixed stress, then you're not going to resist additional motion in those dimensions. It's only if you apply a variable stress to set the strain equal to 0 that you are totally resisting the motion with like a reactionary stress as you would at a support. Okay. So let's go ahead and build this up. I'm just going to compress this practice problem file over here a bit so that we can see it while we're working on the problem, on the solution. So we don't need to do any matrix inverses or anything, but we still are going to want to have this kind of matrix algebra type stuff, and maybe we'll need this sequencing thing later for when we put this into FlexPDE. But let's, instead of saying C matrix is defined with an inverse, let's just go ahead and type out what the C matrix is. So we'll say that this is equal to, and we'll suppress this for now, C matrix is a matrix that's given by these components. And what we can do is we can not write it out in gigapascals every single term, just write it out with 85, 35, 34, etc., and then multiply it by 10 to the 9 afterwards. So let's go ahead and do that. 85, 35, 34, 0, -2, 0, etc. Much like a cooking show, I've gone and prepared this thing typed in part, but I'm going to show you some of the steps: 0, 0, 0, 21, 0, -5, and -2, -8, -3, 0, 28, 0, and 0, 0, 0, -5, 0, 29. Okay, so there is our C matrix put in, but we need this to be in gigapascal, so I'll first just have a look at it. That looks beautiful, and now we'll say times 1E9, and it's a lot harder to see, so maybe better to have it inspected like this first, just to make sure we didn't make any mistakes. Is it nice and symmetric? Yes, looks good. 85, 63, 58. Oh wait, 85. Aha, a mistake. 82. Should have been 82. 82, 63, 58. Yeah, 35, 35, 34. -2, 8, 3, 21, 28, 29. -5, -5. Okay, looks Good. There's our C matrix all typed in. And now we can say, all right, I don't need to look at that anymore. Well, you know what? Let's just leave it as is for now. And when we output this into FlexPDE later, we'll say C blah blah is equal to C matrix times 1E9 to get it to convert all of those into gigapascals all at once. Isn't that great? There's another trick that you can do. So you can remember that this is going to be in gigapascal and gigapascals, sure, gigapascal, and still see it kind of nice like this, but then have all of the things reported later in nice clean equations. All right, we know that the stiffness matrix is going to be relating the stress vector to the strain vector. So we can say sigma is equal to Sx, Sy, Sz, Syz, Sxz, Sxy, and the strain matrix is epsilon, which is, or maybe we'll call this just stress. Stress vector, strain, sure. Epsilon x, epsilon y, epsilon z, and epsilon yz, actually gamma, gamma yz, gamma xz, and gamma xy, the engineering strain for the last components. Now we've got that stress is equal to C dot strain. That's our relationship this time. Oh, I called it C matrix. C matrix. Okay, for real, still not real. I got to spell matrix correctly. C matrix. And now once we've done it correctly, that also shows you out some stuff. It'll multiply it unless you put in the wrong symbol. So if you just see it echoing C matrix times this, why is it not multiplying? Well, the reason is we spelt it wrong. So it doesn't recognize that symbol, and it just says, okay, I guess it's equal to that, man. Yeah. Here we go. We've got it multiplied through. So this is the relationship that we have for this particular material. You see some anisotropic coupling showing up where we have more than 3 components here because of those extra ones in the 5th column. And the 5th row means we've got some extra stuff going on for SXZ. Let's see, in this particular case, we've got that the material is constrained to have no displacement in the y direction anywhere. And as we talked through before, this means that epsilon y is going to be 0, but doesn't tell us anything about the shear components. So this one involves some y displacement, but we could also have it from just z displacement per step, a slope of that per step in y. And same with this one, we could have it with x displacement per step in y. So that doesn't tell us anything about those things. It does tell us that sy is that epsilon y is 0 and sy is going to be whatever it needs to be to hold it still. So if we rerun this, then we've got a bit of a simplified thing here because we know there's no y-directed strain. What next? We know also that we have the 2 x surfaces given a 1 megapascal compressive stress. So that tells us that we have, well, hold on a second. We have this term, so these are in gigapascals on the right-hand side. So on the left-hand side, this is getting a little bit complicated, and you might have just wanted to put this in pascals to keep it all straight already. But on the left-hand side, with 1 megapascal compressive stress, in terms of gigapascals, that's 0.001, and compressive means it's negative 0.001. So that's what we know so far. We still have too many unknowns to be able to solve for stuff, so we have to work out some other things. The other piece of information we need is the fact that it's free to move in the x and z direction. So we were given this compressive stress on the x surfaces, but otherwise it's free to move on those surfaces and deform there. So we're not going to be resisting xy shear or xz shear or even yz shear or z stress. So that means all of those things are equal to 0. And this is the set of equations that we have now. So we could go and rewrite this in terms of the compliance matrix instead of the stiffness matrix, and then have a more easy writing across and solving for things. But there's not really a need to do this. We could say that our equations, maybe Hooke's law equations are equal to this, and then go and pull out each one of them and solve them. Let's try solve sequence Hooke's law equate. Oh, this is always complicated. Sequence of Hooke's law equations. So what do we want? We want the left-hand side of this Hooke's law equation. So we'll say left-hand side of that thing, n equals 1 to 6. That should give us just all of those things on the left-hand side written out. So what we're going to do is we're going to set that is equal to the right-hand side of the same Hooke's law equations, and now we should have each equation. So let's see, is the first one this equals that? Yep. And then the second one is sy equals that. Okay. So here we go. We've pulled out all of those equations, and now we can solve it. Solve this. We'll just put them in square brackets so that we're giving it as the first argument to the solve command. And we've got solutions for everything. So this says under this set of circumstances, we should have gyz is 0, gxz is 0, gxy is 0, xz ends up being this. So we have that strain showing up. We don't have any shear strain in xy or yz. We do end up having a y-directed stress showing up, and we've got a strain in the z direction and a strain in the x direction. Notice that the x-directed strain is compressive. It would have to be from applying this compressive stress in the material. It would be very weird if that didn't couple to a compressive strain in x. The rest of this is a little bit more complicated because we fixed it in y. We have a compressive stress showing up in y as well through the Poisson's ratio, so that kind of makes sense. What about the other two? This one and this one are pretty difficult to think through. What this means is we have, okay, well, actually this one's not so bad. You compress it in x and it can't expand in y, so we need to put on a compressive stress in y as well, and that's where this comes from, but it can expand in z, so it gets some tensile strain in z. This thing here is a little bit more complicated. Why do we have an xz shear strain? Well, the xz shear strain, to see where the strain comes from, we need to, it's easiest if we look at not the stiffness matrix, but the compliance matrix. So let's find S and see what that looks like by taking the inverse of C. S matrix is equal to matrix inverse of C matrix. Okay, so the compliance matrix, what is going to be giving us the xz shear strain? It's going to be coming from, if we go back to our notes, xz shear strain, based on the stresses, it could be coming from xx stress from this component directly. It could be coming from the y stress from this component directly, or it could be coming from the shear stresses. Now, those other stresses are equal to 0. So that's not where it's coming from in this problem. But from how we set it up, we ended up with a compressive stress in both of those things. And since we had negative components there in, oh, wait a minute, hold, that was what those, I was thinking of the stiffness matrix. So we have a negative component there and a positive component there, and this one's bigger. And that tells us that we should have, from the negative y stress that's showing up, this is a little bit complicated. We have a negative y stress and this component's bigger, but the x stress that we applied was a lot larger, so that means that the x term will probably dominate. Yeah, this is only 5 times as big as this. Oh, but wait a minute. This is also only a little bit less than 5 times as big as that. So it looks like we're going to be getting an XZ shear stress, but it's a little bit complicated to tell whether it should be positive or negative because these two terms are generating differently directed things towards it. Let's write that out. Let's say the strain is equal to S matrix dotted with stress, and see what that looks like. So without having solved for anything, we can see that the XZ shear strain is going to be dependent on the Y shear stress. Oh, here's a matrix explorer or vector browser, I guess. If you double click on some of these outputs, some weird stuff is happening. And that depends on the, so the Y shear stress and the compressive one here, and Y shear stress is ending up being compressive. So if we were to assign this stuff, then we'll find out that overall it ends up being negative due to the particular values that the Y axial stress ended up having. So that's how you can take the set of material parameters and incorporate them into determining what the stress and strain need to be when you're given enough of the parameters of boundary conditions that the material is in. So in this case, we are told that we have this compressive stress in X, and it's free in all the dimensions, except that it's fixed to have no Y displacement, and that leads to information about what a lot of the stresses are, but only one of the strains. If you knew that it was fixed in 2 dimensions, that would also be fixing some of those shear strains. It didn't completely eliminate some of them this way. They just happen to end up being 0 because of how we were loading this material and its anisotropy. Next up, we can build up our FlexPDE solution. So we're going to take this set of code that we were working with in the lecture notes and modify it, saving it as the general elasticity practice problem. Sure, okay, 2019 T11. That looks good. Now, what do we need to do? We need to input the size of the thing. So this one, we didn't even care about that in Maple because it just asked us to figure out the resulting axial and shear strains and Y stress that shows up. The strains should be unitless, and the stress is in gigapascals. So we had 0.00023 in gigapascals, and that means that we have 232 kPa as the stress that's showing up. How do we do this in FlexPDE? Well, we are going to have to put in this particular material's stiffness components, and let's now actually ask it to output what those are. So indeed, we have the C matrix expressed in gigapascals. So when we multiply it by 1E9, we're going to be getting the units out of this like we needed. So this is going to be now in pascals, which is what we want to do for putting this into FlexPDE, so we don't have to think about those that unit transformation stuff. We're not going to be looking at this anyway like we were in Maple, so there's no need to scale it to be in gigapascals so the matrix shows up more clearly. We're not even going to look at the matrix. Okay, next up, we have the dimensions. It's a 10 centimeter cube. It shouldn't matter for what the strains are, but that's let's just put it in with the actual size so we can get a picture of what we're looking at here. Next, we have to have that it has no Y displacement anywhere. So on all of the surfaces, on the bottom and the top and the sides and everything, we're going to say value of V is 0. So we'll say value V is 0, value V is 0 there, and that's going to exist across the whole thing. So no displacement in the Y direction. What else do we have? We have a fixed compressive stress in the X direction on which surfaces? The two X surfaces, which would be, let's see, this is a Y surface because we're holding Y to 0 between there and there. The next one is an x surface. This is the x equals Lx surface. So we'll say load of u is equal to negative, it's the positive x surface, the x equals Lx surface. So to do a compressive one, we'll go negative 1e6 stress, right? Negative 1 megapascal of stress, the 1 megapascal of compressive stress. Then we'll take that off on the top y surface, and we'll put it back on load u is equal to 1e6 on the x equals 0 surface. Okay, so this should now be, if we haven't forgotten anything, deforming the thing. Wow, that's quite a lot of deformation. I wonder why the scaling factor is doing it this way. Let's see if something else is going a little bit weird with this. Did we keep anything in the differential equations? No, looks good. Yeah. Oh, we maybe forgot to... Oh, these shouldn't matter, actually. So if we haven't made any mistakes, we can get rid of this stuff and run it again. Yep, okay. Now let's just compare and report what we have in the center and see how that compares with what we got in Maple. The big things to report are the strains and the stresses in the center. So let's have a look under report, and we'll make a report of Lx over 2, Ly over 2, Lz over 2, and we'll look at Gxy, Gxz. We'll need 6 reports. Next one we're going to look at is Gyz as well. That should be 0. Gxz. What did we do? Hold on. Gxy, Gyz, Gxz is the third one. Then we need Sy and epsilon z. Did we call that epz or just Ez in here? Ez. And finally, epsilon x. So Ex. We don't need to report theta anymore. Let's just have a look at this in the center and see what we get. So in the center of the thing, it looks like we've got 0, 0, negative 1.4 e minus 7, which is 0.14 e minus 6, so that agrees. And then 232 kPa, compressive for the y stress, and 9.4 e minus 6 for epsilon z, the z-directed axial stress, and the x-directed axial stress, 1.6 e minus 5. So it agrees perfectly, even though we built up the thing very differently. Let's have a look at reducing this magnification and see if we can make the plot a little bit more clear. So this is now only showing 10% of the global displacement. So the cube seems to be compressing a bit and doesn't need to shear except for the one shear direction that it developed, which was a little bit of XZ shear. So if we were to look at the XZ face, which should be this face, yeah, it's sort of subtle. You can see that it's kind of moved together there and moved together there as well. If we put the magnification back to 0.3, then it's a lot more prominent. Let's have a look at that face. Yeah, you can see a bit more clearly that it is shearing on that face. It's got an XZ shear because we've got this angle is increased and this angle has decreased. Also, it has compressed in the X direction axially, but stretched in the Z direction, and the compression in the X direction is more prominent than the stretch in the Z direction, and this compressive stuff is what's making the thing look so much more extreme when we magnify that displacement so that we can see it. This is we have to be careful if we kind of multiply the displacement by 2. So if we have this relative magnification factor going on right now, where we say whatever the maximum magnitude of position was originally, and then divide that by the maximum displacement. So this is scaling the maximum displacement to be 1/3 of the maximum position. So if we were to take this thing and then multiply it by 50%, we might get the cube to kind of fold into nothingness and go and extend in the other direction, right? Increasing this more is going to make the cube look like it's getting larger and not moving as much, but that's because it's folded in on itself. So the displacement is really extreme in this case, and the magnification factor we're usually using is perhaps a bit misleading and not the best thing to do if you were to have like a 50% magnification factor here. The final part of the question asks us whether or not the stress and strain should be uniform. So certainly when we did the calculation in Maple, we assumed that the stress and strain were uniform. In order to be able to solve this, we said that the stresses that we're applying on the exterior are going to map all the way through and still be those stresses in the center. And the fact that FlexPDE perfectly agreed with Maple likely means that the stresses and strains are uniform, but why should they be? So for this problem, we are applying a compressive stress in X, and we are allowing any deformation except deformation in Y. We're fixing Y, and this is going to lead to compressive stresses in Y. Now this material does have some strange sorts of shears showing up, but the strange shears that show up as a result of this loading only need to be in the XZ direction. And since those surfaces are totally free, we can have uniform strain happening everywhere. We're not ever stopping the Z displacement or the X displacement, so this ends up being completely uniform. Let's have a look in FlexPDE at what this uniformity looks like. If we take a contour plot on, let's say, Z equals LZ over 2, we'll look in the middle of this material at what the deformations are, for example, then the deformations are increasing linearly, right, in X and Z on this surface, and the Y deformation is just 0 because we're fixed to have none of that in any different direction. Rather than looking at the deformations, you can look at the strains, epsilon X, epsilon Y, and epsilon Z, or perhaps the stresses, but let's just look at the strains all on this surface. It was EX, EY, EZ, and GX, GY, G, G, YZ, GXZ, GXY. So across the center, we have uniform strains everywhere. See how these are all just fixed at some value? So we have a prominent X-directed strain, which is fixed. We have a prominent Z-directed strain, which is fixed. We have no Y-directed strain. So this helps us figure out that and confirm that the stresses and strains that we had in this material because of this loading ended up being uniform. Let's think about what's going on here. We said you can't move in Y. You're fixed to the value you had in Y, and we're going to put a stress in X and Z. And that led to it needing to shear in X and Z because of how the material couples things. But that's fine. It didn't try to shear in Y, so we're okay. Let's explore some boundary conditions that can give us a bit of trouble though. This material has some interesting stuff going on in the XZ plane. So that will be at fixed Y values. Instead of plotting at Z equals LZ over 2, let's plot at a Y value and see what's going on in this surface. So still everything's uniform generally. These are just zeros. That's why it looks kind of funny. But let's have a change in the boundary conditions. Let's imagine that we try to, instead of fixing Y equal to 0, we're going to be fixing X equal to 0 and push on it in the y direction, which will be pushing on this front face to see what happens, see how the XZ shear strain shows up. So we'll switch up some roles of X and Y here by saying value of U is equal to 0 on the top and the bottom, and then value of U is equal to 0 all around the edges. And now we're going to put a load on V that is in the positive direction. Load V is 1e6. Load V is 0 on the sides. Load V is negative 1e6 on the top. And load V is 0 on the other side. And now let's look at this center V surface there. We've got some shear happening, some prominent XZ shear when we put in those that compressive stress in the y direction that's into the page here, because this is the XZ plane, and ended up with uniform looking stresses showing up, uniform looking strains showing up in all of the different directions. Suppose we manage to fix it a little bit differently though. So on this surface, it's wanting to do that that strain, but what if we said that it's not allowed to move in Z all along this bottom line, right? So we just say, you know what, the entire bottom of this thing starts 0, 0. We're going to have a bit of a non-uniform boundary condition. Value of W, line to value of W is equal to 0, and then we get rid of that on the next one. We say, you know what, be free W, load W is equal to 0. Now what happens? Aha. So by messing with the boundary condition and getting the asymmetry of this thing along the XY plane, we just took one surface and said, you're not allowed to move in W. Which one did we actually take? We took the very first one, which is from 0, 0 to LX 0. And that is at all Z's, 0, 0 to LX 0, which should be, the XY plane is in the bottom actually. We took one side of it and said you're not allowed to move in Z. And let's rotate this and see what that surface is. So it looks like this is X equals 0 and 0.012 X, Y, Z is going up. So the corner here, we took this first corner, 0, 0, to LX 0, which means we took this line and said you're not allowed to move in Z. And just by doing that, we've ended up with a lot of asymmetry showing up in this problem in kind of an unpredictable way. So with this set of boundary conditions, where it's not like a uniform setup, but just one of the surfaces that's fixed in a direction that isn't the case on the other ones, like this front line, you see it's not able to move up and down, but the side of it has wanted to shear as a result. Now we've ended up with a very strange setup happening in this material from the non-uniform boundary conditions. So for Maple to really agree with what's going on in Flex, you have to have boundary conditions that set up the problem so that you're going to be experiencing uniform stress and strain in it. And especially with materials that have anisotropic matrices, that can be complicated. This might seem like a big inconvenient thing in FlexPDE when we're looking at it like this, but think about what we're able to do. Even for a ridiculous asymmetry of matrix components and a weird asymmetry of boundary conditions, we can figure out what the stresses and strains are everywhere using the finite element method, and we can understand how they generally should behave by incorporating our analytical approaches to this and make things easier using computers all along the way. I hope that this has been entertaining, that you've gotten something out of this, some piece of information, and mostly just the tools to go off and explore and see how materials will bend and try and get your head around these things for anisotropic materials and use it to engineer some cool devices. Thanks for watching. See you next time.